In this video, we're going to look through example 2 in section 5.1 and 5.2 on the second fundamental theorem of calculus. So in example 2, we're given the opportunity to explore the second fundamental theorem of calculus graphically. So let's read the question together. So example 2 says, suppose that f of x is given by the graph below. So here's f of x. And let a of x be defined as the integral of f from -1 to x. Then part A says, what is the relationship between a of x and f of x? So again, we're given a of x as defined, is a function defined by the integral involving f. So part A, we're just going to use that second fundamental theorem of calculus to relate these two functions. So by the second fundamental theorem of calculus, we know that the derivative of a of x, which is the derivative of the integral from -1 to x of f of t dt, is equal to f of x. So in other words, we can say f of x is the derivative of big A of x. In other words, a of x is an antiderivative of f of x. So here we're just practicing using the statement of the second fundamental theorem of calculus and practicing some of our new vocabulary here, antiderivatives. Okay, so that was sort of some abstract big picture relating big A and f. But let's get a deeper sense for what this function a of x is. And to do that, let's look at part B. So part B says, complete the table below with the exact values of big A of x. Then sketch a rough graph of a of x on the blank axis provided above. So let's do a few together, a few values of a of x together, and then I'd like you to try some on your own. All right, so this is going to be fun. Let's get into it. So we're looking at first computing a of -1. So a of -1. So recall, a of x is defined by this integral. I'm even going to highlight it here so we can really sit with it. So a of -1 would be the integral from -1 to -1. Wherever I saw x in the function, I'm going to put a -1 of f of t dt. Well, the integral, where our limits or our bounds are the same value, -1 to 1, just going to have an area of 0. So f of x, it does start for us at -1, but the area under -1 is 0. Okay, that's not too bad. So we can just fill in 0 here. Okay, so now let's look at a of 0. So that's going to be the integral from -1 to 0 of f of t dt. So let's look at our f function. From -1 to 0, our function f of x is at 0. So the area under that curve is also 0 again. There's no area there. Okay, not bad. Let's do one more together. A of 1 is going to be the integral from -1 to +1 of f of t dt. So let's consult our f graph again. So now we're looking at the integral of f from -1 to 1. So the area under f from -1 to 1. So it'll be this area here. Okay, so we can compute that. This first part, again, has a zero area. So we just need to compute the area of this little triangle. So we see that each tick mark here is representing one whole unit. So this triangle is 2 high, a width of 1. So the area would be 2 times 1 times a half. Area of a triangle is 1/2 base times height. So we could fill that in 1/2 base times height, which would give us 1. So a of 1 is 1. All right, so now I'd like you to pause the video and see if you can fill in a few more of these values of a of x. And then when you're ready, play the video and we'll compare our work. All right, so after you calculate those integrals or those output values for a, you should be getting for a of 2 should be 1. A of 3 is negative 0.5. A of 4, negative 1. A of 5, negative 0.5. A of 6 should be 1, and A of 7 should be 3. So let's just check a couple of these together to make sure we're on the right track. All right, why don't we check? We'll check A of 3 and A of 6. So let's start by checking A of 3. So A of 3 is equal to the integral from negative 1 to 3 of f of t dt. So let's look at our f function to determine what that area will be. So the integral will be the area under the curve. So we'll have area here that we need to calculate, and then we're going to subtract the area here. Because recall, any time the area that we are computing is below the x-axis, we're going to have a negative area. All right, so we can notice that this line of our function is a linear line. And if we go down 1, 2, 3, 4, we go over 1. So the relationship is down 4 over 1. It's a linear relationship, which means if we go only halfway down, we go only halfway over. So this point here happens at 1.5. So then the area of the first triangle has a base of 1.5 and a height of 2. So the area is going to be 1/2 times 2 times 1.5. So now let's look at the next bit of area. So we can see that this next area we can divide into some parts to help it be a little bit easier. So we see that we have a triangle here. We have a square here and a little triangle here. So we can break it up into these 3 parts. So the first triangle is going to have a base of just 1/2 or 0.5 and a height of 2. So the area of that little triangle will be 1/2 2 times 0.5. This square here we see is units 1, 1, and 1, or just 1 and 1, 2 sides determine the square. So the area there is just going to be 1 unit squared. And we have this little triangle here. And we see it has a base of 1, a height of 1. So the area will be 1/2, 1 times 1. Okay, so now we have these 3 parts giving us the area that we want to compute. So let's put all of those together. So we have, let me get out my blue again. So we have 1/2 times 2 times 1.5. That's the area of the first triangle. Then I'm going to subtract 1/2 times 2 times 0.5. Subtract another 1/2 times 1 times 1. And subtract my final 1 square. Okay, so let's go ahead and simplify this a bit. So my 1/2 and 2 cancel out here. My 1/2 and 2 cancels out here. So what else am I left with? I'm left with 1.5 minus 0.5 minus 0.5. This 1/2 is equivalent to 0.5 minus 1. All right, so then I can subtract here. So to do that, I see that 0.5 times 0.5 is negative 1. So I get 1.5 minus 1 is 1.5 minus 2, which is negative 0.5. So my area here is negative 0.5, which is what we are getting there. All right, let's just do one more here. We're going to do A of 6. Erase a little bit of work here. So let's keep in mind that we know the integral from negative 1 to 3 already. And now we're just going to continue looking at the area under F until we reach 6. So we can start with our value for A of 3. and then subtract now this little area of this triangle and add the area of this triangle. So the area of this smaller triangle is, again, it's a triangle of length 1, base 1, height 1. So that would be 1/2, 1 by 1. Then the bigger triangle has a base of 2 and a height of 2. So just 1/2, 2 by 2. Okay, so then filling in a of 6. A of 6 is the integral from -3 to 6 of f of t, which we know is negative 0.5 plus the integral from 3 to 6 f of t dt. So that would be the negative 0.5. We're going to subtract that 1/2, 1 times 1, that little triangle, and add the blue triangle, 1/2, 2 by 2. So for that, simplifying things here, we get negative 0.5 minus 0.5 plus, cancel out a 2 and a 1/2, plus 2, which just becomes negative 1 plus 2, which becomes 1. So we should get that a of 6 is 1. Awesome. Okay, feel free to check the rest of them just to make sure you've done your calculations correct. It's really easy to mislabel one of the shapes that you're looking at. So take another shot at it if any of those outputs are different than what I have here. Okay, so now let's try to draw a rough sketch of a of x using the table here. So what I'm going to do is label my points. So a of -1 is 0, so I get 0 here. A of 0 is 0. A of 1 is 1, so I'm up here. A of 2 is also 1. A of 3 is negative 0.5. So I'm down here. A of 4 is -1. A of 5 is negative 0.5, so I'm back up here. A of 6 is 1, and A of 7 is 3. So I'm up here. Okay, so now I've plotted the points, but the question is, what happens between the points? Or how are the points connected? Are they connected just straight with straight lines? Are they connected by a smooth curve? So that's our question. So we are going to explore that in the next video, but what I'd like you to do is think about it on your own first. Think about what the graph should look like in between these points. And then we'll meet again in the next video.